Yeah, let's check that everything is working correctly. Let's also see if anyone wants to join in. So I'm happy to answer any questions about this website, biomedical.com. Go check it out if you haven't done so already. Pop the link in the chat. Any questions relevant to the website, welcome. Keep repeating myself, but let's see if anyone wants to join in. We should have prompts for pretty much everything. Yes, we actually took one of the earlier conversations we had with one of the bots, turned it into Notebook LM podcast. So this will be two hosts, talking to one another. Just listen to it, and there's a option to intervene as well if something goes really wrong. But surely they will be doing pretty well.
Waveforms, endless numbers, and just wished you could kind of feel what was going on.
Mm.
Well, today we're plunging into the deep end with Biomedical. It's a website designed to do, well, exactly that, translate that intricate data into accessible, interactive experiences.
It really tries to turn that abstract data into something you can properly engage with.
Like something you can really get your hands on, or maybe your ears on, as we'll see.
And what's really compelling here, I think, is moving beyond just passively looking at data.
Right.
Bionic Chaos gives you tools to actually manipulate and experience these biomedical signals directly. It fosters a much more intuitive understanding.
Exactly. And look, we're not just scratching the surface today. We are going deep, properly deep into the technical side of two specific tools on the site.
Okay.
The EEG to music converter and the ECG synthetic signal generator. And all our info, it's coming straight from the Bionic Chaos site itself. It's put together by a biomedical data scientist, lots of experience.
And importantly, everything's open source.
Yes, crucial point. So if you like to tinker, understand how things really work under the hood, it's all there.
That open source aspect is, well, it's a huge advantage. Transparency, validation, it encourages people to build on it, contribute back. It's how science should ideally work, right?
Absolutely. So our goal isn't just, listing features bullet point style. We want to unpack the how and the why.
Mm-hmm.
How do these tools actually function? What are the principles and what insights can they genuinely give us?
Sounds good. Where are we starting?
Okay, let's kick off with, I think, the really fascinating one, the EEG to music converter. Imagine turning brain waves, the actual electrical activity, into something you can see and hear.
Yeah.
So this tool, it takes data from 16 EEG channels and translates it. Visually, you get time domain, frequency domain plots, but also you get this unique auditory experience.
And presenting it visually and auditorily at the same time, that's clever. It plays to how our brain processes information across different senses.
Ah, interesting.
You might actually hear a pattern or an anomaly that you might miss just looking at the graphs. It's a multisensory approach to exploring the data.
And it's not just static. The graphs are interactive. You can pick which channels you want to see, adjust the time window like a quick 1-second snapshot, or zoom out to a full minute.
60 seconds, yeah.
But here's where it gets technically really interesting, I think. The actual EEG to music part, it has these options, auto volume and auto duration.
Right.
And these dynamically adjust the music based on the energy within different brainwave frequency bands, delta, theta, alpha, beta, etc.
That automated adjustment is quite a sophisticated feature. It suggests some kind of mapping, maybe higher energy in a band means louder sound, or perhaps a longer note.
That's the idea, yeah.
It could give you a really intuitive feel for shifts in brain activity, highlighting when certain oscillations become dominant.
And for even finer control, technically speaking, there are filters. You've got a wavelet and noise filter that helps clean up the raw signal, reduce artifacts.
Which is crucial for EEG.
Definitely. And then there's a bandpass filter. Now, this is like tuning a radio, right? But here you can adjust the filter order from 1 to 4. What does increasing that order actually achieve, technically?
Okay, so a higher filter order gives you a sharper cutoff. It means the filter is more effective at isolating just the frequency band you're interested in and rejecting everything else outside that band.
So it's more precise, like a finer sieve.
Exactly. A higher order filter is more selective. It does a better job separating the signal from the noise.
Got it. Makes sense. There's also this whole spectrum toggle. It overlays frequencies below 0.5 hertz and above 30 hertz onto the model view. We usually focus on delta, theta, alpha, beta, so why look at this wider range?
Well, looking beyond those standard bands lets you explore slower oscillations or much faster ones that might be relevant in certain conditions, maybe certain pathologies, but often get filtered out or ignored.
I see.
It gives you a slightly more complete picture of the brain's electrical landscape, potentially revealing some subtle dynamics.
And visually, you can switch the frequency scale, linear or logarithmic. When would you choose one over the other?
A linear scale shows all frequencies equally spaced, good for seeing absolute power. But a log scale compresses the higher frequencies. This lets you see the details in the lower frequency bands, like delta, which often have much higher power, with them totally dominating the whole graph.
Right, so it helps visualize the lower end better.
Yeah, especially when there's a big power difference across the spectrum.
Okay. And below all these controls, you have the raw signal chart, the familiar squiggly lines, voltage over time, time domain. And then the spectrum chart, that's the frequency domain breakdown showing the power in delta, zero point 0.5 for 8 hertz, theta, 4 to 8 hertz, alpha, 8 to 13 hertz, and beta, 1330 hertz.
Those key bands.
And the actual data behind this, it's intracranial EEG data from Neurovista. It's publicly available on ees.org, so anyone can actually go and look at the source data.
And using intracranial data is significant. Because the electrodes are right on the brain surface, the signal quality is generally much higher. Less noise, more detail compared to scalp EEG.
Oh, right.
So making that kind of research-grade data explorable like this, that's a powerful teaching tool.
Okay, let's dig into some of the technical discussion points that came up. Looking at this frequency spectrum displays, you see the power split across the bands. Sometimes delta seemed quite dominant in the examples. Mechanistically, what could cause such high power specifically in the delta range?
Well,
Oh, hey, our listener wants to join in. What's up?
Can we address an issue? So the original source for the data is seem to be not available anymore. The ieeg.org website is down, so I would assume it's not coming back. Can you comment on that?
oh, that's an important point you raised. Thanks for letting us know about ee.org. It seems the original source might be temporarily unavailable at the moment.
Right, that's a bit of a snag. We want to make sure everything we're discussing is fully transparent. The Biomedical page does mention that the data is from Neurovista, which was available on ee.org.
And while the direct link might be down right now, the principle of using real-world data, especially intracranial EEG, remains a key strength of the tool for understanding brain activity.
Absolutely, and it's worth remembering that many research data sets do get hosted on various platforms over time. The crucial thing is that the tool is built on real data.
Indeed, the ability to visualize and sonify actual brain recordings is still the core function here, even if the original source website is temporarily offline.
Okay, so with that important clarification, let's get back to some of the finer technical details of the EEG to music converter.
Yeah, you can see how it's currently mapping EEG power to musical notes, but the rhythm seems just tied to scrolling through the data window.
Right, so this raises some technical questions. How is power actually mapped to pitch? Is it just linear, higher power equals higher pitch, or something more weighted?
That's a critical design choice for any sonification. Linear mapping is simple, but maybe it doesn't capture the perceptual importance of changes equally across bands.
Hmm.
You could imagine a weighted approach, maybe giving more influence to, say, alpha changes if you're interested in relaxation states.
And what about normalizing across the 16 channels if one channel is way noisier or has much higher amplitude?
It could dominate the whole musical output, yeah. Normalization across channels is pretty essential to get a balanced representation of the overall brain activity, rather than letting one channel skew.
Yeah, just resize the notebook LM window and stop the playing. Let's see if we can continue from the same point where we left off.
Ever stared at a screen full of biomedical?
No, it's starting from the beginning. It's doing really, really well. Yeah, there's some obvious things that we must have not explained in the text. Yeah, let me know if you want to see another one of those applications with different data, synthetic data, or perhaps your own data, or another publicly available data set.
Yeah, normalization across channels is pretty essential to get a balanced representation of pathologies.
Okay.
It reflects large groups of neurons firing in sync. Using intracranial data is significant. This lets you see the details in the lower frequency bands, like delta, which often have much higher power, without them totally dominating the whole graph.
Right, so it helps visualize the lower end better.
Yeah, especially when there's a big power difference across the spectrum.
Okay, and below all these controls, you have the raw signal chart, the familiar squiggly lines, voltage over time, time domain, and then the spectrum chart. That's the frequency domain breakdown showing the power in delta, 0.54 hertz is theta, 4 to 8 hertz, alpha, 813 hertz, and beta, 1330 hertz.
Those key bands.
And the actual data behind this, it's intracranial EEG data
Yeah.
from NeuroVista. It's publicly available on iag.org, so anyone can actually go and look at the source data.
And using intracranial data is significant. Because the electrodes are right on the brain surface, the signal quality is generally much higher. Less noise, more detail compared to scalp EEG.
Ah, right.
So making that kind of research-grade data explorable like this, that's a powerful teaching tool.
Okay, let's dig into some of the technical discussion points that came up. Looking at those frequency spectrum displays, you see the power split across the bands. Sometimes delta seemed quite dominant in the examples. Mechanistically, what could cause such high power, specifically in the delta range?
Well, dominant delta activity usually points to slower brainwave frequencies. You see that in deep sleep, under anesthesia, or sometimes with certain brain injuries or pathologies.
Okay.
It reflects large groups of neurons firing in sync. So seeing that dominance visually and maybe hearing it translated musically could give a more immediate sense of that underlying brain state.
Now, a really granular point. If you actually look in your web browser's developer console while this tool is running.
Ah, okay, under the hood.
Yeah. You can see how it's currently mapping EEG power to musical notes, but the rhythm seems just tied to scrolling through the data window.
Right.
So this raises some technical questions. How is power actually mapped to pitch? Is it just linear, higher power equals higher pitch?
Yeah.
Or something more weighted?
That's a critical design choice for any sonification. Linear mapping is simple, but maybe it doesn't capture the perceptual importance of changes equally across bands. You could imagine a weighted approach, maybe giving more influence to, say, alpha changes if you're interested in relaxation states.
And what about normalizing across the 16 channels? If one channel is way noisier or has
Yeah.
much higher amplitude.
It could dominate the whole musical output, yeah. Normalization across channels is pretty essential to get a balanced representation of the overall brain activity rather than letting one channel skew everything.
Definitely. And those auto volume and auto duration features, they're driven by energy in each band. Can we guess at the algorithms? Is it like a threshold, energy crosses X, volume goes up?
Probably some kind of dynamic scaling based on maybe instantaneous power or power averaged over a short time window. A threshold is possible, but maybe a smoother continuous mapping where changes in energy gently modulate volume and duration.
Yeah.
And actually seeing that happen visually in the interface,
Yep.
like a little volume meter per band, that would be really helpful for the user.
Absolutely. Which leads perfectly into the planned future improvements for this tool. First up, making it clearer in the interface how auto volume works.
Good idea.
Then, as we just said, adding some kind of visual indicator for those real-time volume changes. Also, exploring mapping rhythm to EEG bands somehow, that could add another layer of information.
Instead of just the scroller, yeah.
Interesting.
On the tech side, converting the data to JSON for the front end,
Yeah.
probably for better performance, making the scroll bar more granular for finer control.
Always useful.
And finally, maybe a channel summary overlay. Something showing the dominant frequency band for each channel at a glance. That sounds like a really useful summary view. These all seem like thoughtful improvements, enhancing usability, adding feedback, exploring richer mappings. It could become an even more powerful tool for learning and exploration.
Okay, so we've journeyed through the soundscape of the brain. Let's switch gears now to a different biological signal. The heart's electrical activity via the ECG synthetic signal generator.
Right.
You can find this one at bionichaos.com/ECGen. And this tool is all about generating artificial ECGs. You get a surprising amount of control over the parameters.
So this is different from the EEG tool. Instead of analyzing real data, you're creating signals.
Exactly. It's designed as a hands-on way to understand the bits and pieces of an ECG signal, see how different factors change its shape. Really useful for teaching, for research, maybe testing algorithms.
That's like a virtual lab for cardiac electrophysiology. You can isolate parameters, see their effect in a controlled way.
Precisely. So what technical knobs can you actually turn here? You can select the ECG signal type, though. Currently, normal is the only option. You adjust the window size, the isoelectric voltage, that's the baseline, 0 to 1 millivolt. There are placeholders for PQRS delay and QRST delay, but they're inactive right now.
We'll come back to those.
You can set the BPM, beats per minute, anywhere from 40 up to 140.
Decent range.
And then you can add noise, different kinds. BPM noise, which simulates an irregular rhythm up to 100 milliV variation. White noise, like general background fuzz, 0 to 0.5 milliV. And that classic 50 hertz noise up to 1 milliV, mimicking power line interference.
And being able to add specific noise types is really valuable. It helps you understand the challenges you face with real ECGs.
Mm.
You see how artifacts can mess up the signal, why you need filtering. Including 50 hertz noise is spot on. It's so common.
Yeah, looking at the examples, you can clearly see that 50 hertz noise adding that sort of high frequency ripple all over the ECG. It's a very clear visual.
Yeah.
Now, that 50 hertz noise, is it likely just implemented as a simple 50 hertz sine wave added onto the signal?
Yes, that's highly probable. It's the standard way to model power line interference. Simple additive sine wave shows the effect clearly.
Okay. Now, about those inactive parameters, the PQRS delay and the QRST delay, when they are implemented, how would they likely work? They'd control the timing between the different parts of the heartbeat signal, right? The P wave, QRS complex, T wave.
Exactly. By letting you adjust those intervals, the tool could simulate different heart conduction problems, like increasing the PQRS delay. That could mimic a first-degree AV block where the signal transmission is slowed down.
Ah, I see.
Or changing the QRST interval could represent issues with ventricular repolarization, maybe linked to ischemia or other conditions. That level of control would seriously boost the tool's ability to model clinically relevant situations.
What about the BPM range, 40 to 140? Covers most adults, sure, but should it maybe be wider for really fast heart rates like some tachycardias? Or even for kids who naturally have faster rates?
That's a fair point. Extending the range would definitely make the simulator more versatile. Including higher rates makes it more relevant for, say, exercise physiology or pediatric cardiology where baseline rates are different. Yeah, broadening it seems like a good idea.
Which leads us neatly into the planned future upgrades for this ECG generator. Top of the list, get those PQRS and QRST delay parameters working.
Essential.
Then evaluate extending that BPM range, as we just discussed. Developing more advanced noise simulation is also on the cards, maybe dynamic noise, or even letting users upload patient-specific noise patterns.
Ooh, user-uploaded noise. That's interesting.
Yeah, and adding more ECG types beyond just normal. Think atrial fibrillation, PVCs, other common arrhythmias. That would hugely increase its educational value.
Definitely. Simulating arrhythmias is key.
And finally, adding real-time annotations, little labels pointing out the PQRS T waves as the signal generates. That would be great visual feedback for learning.
Absolutely. All these planned updates show a real commitment to making this a more comprehensive, clinically relevant tool.
Yeah.
It could become pretty indispensable for students, researchers, algorithm developers,
Yeah.
a wide audience.
So let's quickly recap our technical deep dive today. We really picked apart two quite sophisticated tools on Bionic Chaos. First, the EEG to music converter, this unique way to experience brain data visually and auditorily.
Yeah, potentially quite insightful.
And second, the ECG synthetic signal generator, a highly flexible platform for understanding heart signals by building and tweaking them yourself.
Both really highlight how interactive tech can make complex biomedical stuff more tangible, more accessible.
And what stands out is the level of technical detail you can actually access and control through these fairly user-friendly interfaces.
Right, they aren't just black boxes. They give you a window into the signal processing and let you really learn by doing, by exploring.
Absolutely. And we really encourage you, the listener, to go check these out for yourself. Explore the tools, dig into the open source code if you're inclined. It's all at bionichaos.com.
Whether you're a student, a researcher, or just curious about how the body works electronically, there's a lot there to engage with.
It really underscores how important accessible, transparent tools are becoming in science and education. Open source platforms like this empower more people to engage with complex data.
Which hopefully leads to deeper understanding and maybe even faster innovation down the line.
Well, thanks for joining us on this really technical exploration today. It's a great reminder that even really complex information can become clearer, maybe even musical with the right tools.
Definitely food for thought.
So here's something to ponder. As these tools get better at translating biological signals into different senses, sound, maybe even touch eventually, what are some of the really unexpected, maybe transformative applications you can imagine for this kind of technology in the future? Think healthcare, maybe even just understanding ourselves better. What could that lead to?
Okay, that was a bit abrupt. What? It didn't sign us out, did it? Well, it's probably a good thing because we can keep going. And we do have another version of this in the works, a much more advanced. So someone's asking, Steven was asking if you can download the synthetic data. So this is Plotly, so whatever functionality you have using Plotly can download plot as an image. That helps. So that works well. I'm pretty sure you will be able to download the data as well. This SVG container. Okay, actually the problem with this tool, with this specific one, is that we have a backend. It's a Flask application. And we have a backend for it. The new version doesn't. Okay, so in the backend we have this Flask application that generates the code. Yeah, I would like to convince ourselves that we should not be doing Flask applications anymore because, well, in most cases we can do everything using JavaScript. So it's just running front end. So that's good for multiple reasons. So obviously ChatGPT can create, well, can create synthetic data as well, but then it can create a tool that will make a data. Just ask. But yes, let's actually jump into so we have that tool running. So this one does not have a backend, which is really nice because I don't have to waste electricity. this one we will potentially have an expert looking at this. Well, currently the best expert we've got is ChatGPT 03. So the smartest, the best model we have access to. Okay, I'm making some games as well for you to explore if you have any younger players. I mean, everything is biomedical data related, isn't it? But back to the ECG. So this is another version of a signal generator. We covered the previous one. It was more basic. Well, I mean, still working pretty well. There's quite a lot of functionality. But someone did ask, well, it was a honeypot, wasn't it? Talking about bees and honeypots. Honeypot in this case has a different meaning. But yeah, we had those grayed out, the PQRS delay and the QRST delay. So someone obviously did ask about it, but it was not implemented in the code. So therefore, we are doing another simulation. In this case, we did focus on those timing intervals. So the original idea of this was that you will have a basic, intermediate, and expert control panels. The expert is so expert that I don't even know what is it about. Yeah, it's something to do with one of the abnormality types. That will be the mobits. That doesn't seem to work. When you select the mobits second degree AV block, should be, those controls should be specifically designed for that. So in general, there meant to be more controls that are specific to each one of those abnormality types. Currently, we don't have that. Not sure how difficult that will be to implement. Oh, and also to the question, Steven's question, if we can get the raw data, or synthetic data. So in this case, yes, you can also download PNG. Yeah, it will look like that. It just has a transparent background, so no background. Or you can download the CSV file as well. So actually you can load it. This data. In this case, only 3 leads are selected, 1, 2, and 3. But then the actual data is 12 leads, as it should be full-fledged ECG recording. So when you download the data, you actually get all the 12 leads for your convenience. But yes, for the display, probably wanna show just a smaller number of leads. Select your window length. Yeah, that was yes, let me know what you think. Any questions, comments are welcome. This is already available on the site. It wasn't just formally published. If you're watching, you will have the link as well. Just share it in the chat so you can go check it out. And we will be popping it on the site, well, because it got quite complex. So it has about 180 lines of JavaScript, just the export function, display, grid handling, work response, regenerate, preset control, populate presets. Okay, there's now worker.js that actually does the a generation of the waveforms. So you have your math exponential functions, so on and so forth. That will actually generate the waveform. Notebook LM didn't actually specify what's the current limit for the number of podcasts that you can generate. But we will be making another one. It's hard to get this stuff working well on a mobile screen. We'll give it a go. I mean, we won't be doing anything. It would be the port. I wonder if this is all in one script. Can you run it in the canvas in ChatGPT? Because then you have access to better models. That's like 2 JavaScript files, presets, JSON, and HTML. So that's probably not practical. There is no CSS though. The CSS is within the HTML, which is good because we can modify it with Copilot. How can we improve the styling for this page so the components are visible well both on larger screens and smaller mobile screens and they scale correctly?
Collecting workspace information. To improve the styling for better visibility and scalability across both larger screens and smaller mobile screens, you can make the following adjustments. 1. Use relative units for sizing. Replace fixed units like px with relative units like m, rem, percent, or vh/vw to ensure components scale properly on different screen sizes. 2. Enhance media queries. Expand the media queries to handle a wider range of screen sizes and orientations. For example, at media, max width, 480px. Dot controls, width, 100%. Height 50 VH. Padding 0.5 rem. Dot plot area. Padding 0.5 rem. Dot grid 12. Grid template columns 1 FR. At media, min width 1024 px. Dot controls. Width 30%. Max width 400 px. Dot plot area. Padding 2 rem. Dot grid.
Not sure why it's reading the code. It's obviously non-comprehensible. Don't need to do that. Let's start implementing one by one, see what we get. Or should we just apply them all at once? Yeah, just have a smarter model, obviously. It knows. Remove all one It's replaced by O3. There's an O3 mini, which is not available in ChatGPT. Okay, there's a couple of things. In plain text, can you explain why when we make the window narrow on a narrow screen, the traces, the waveforms are not visible anymore? Can you explain?
The issue likely arises because the CSS styles or layout of the page are not responsive to narrow screens. Specifically, grid or flexbox layout, the .grid 12 class uses grid template columns, repeat, 4, 1FR, which creates 4 equal width columns. On narrow screens, this layout might.
Okay, can we fix it? Let's go O3 mini. So that moved it into the edits tab. No, we are not editing that. Hey, can you redo? We're just looking at this specific file. Nothing else. Why are you adding files to it? Why are you adding files to it? Are you kidding me? We are just adding this. We're just editing this specific file and nothing else. Can you update as discussed before?
Step by step. Change the page title in the head section from ECG Simulator to ECG Simulator v3. Update the meta publish _date from May 14, 2025 to October 27, 2023. Index.html. Existing code. Head. Metacharsa equals UTF-8. Existing code. Title.
Yeah, that's all free. All free mini. Let's just go GPT-4. Oh, there's something wrong with the implementation. Don't understand why it keeps adding files to the mix. Can we fix it in this specific file? Don't edit anything else.
Index.html. Fix the following issues. Correct the main.body CSS.
Okay, I can do it quietly as well. Now it seems to be editing the correct thing, which is a plus. Okay, can we try to improve the styling for this page? Can we make sure that the waveforms are visible regardless of the screen size?
Index.html.
Because at least we're editing the correct file. Okay, the grid 1, 2. Okay, we added more styling. Yeah, interestingly, it did multiple changes. Right. What if we just get rid of all the styling? We need to redo it. How do we redo the styling for the page, potentially simplifying it and making it work on any screen size, including mobile?
Collecting workspace information to simplify and make the styling responsive for all screen sizes, including mobile. You can use a combination of CSS Flexbox and media queries. Here's how you can approach it. Update the navigation menu. Use Flexbox to align the logo and menu items.
The thing is, we need to figure out which model to use. Which model to use? Okay, we need to add the styling within each component. So we do have the styling for the whole website. That's the external CSS. But then we need the components that are specific to this web applications would be missing from the global CSS. So we need to have the styling for each specific page, for each specific component within this application.
Index.html. Add A and LT. Style.
Do we have a footer? I don't think we have a footer. Okay, let's accept that. Remove all the footers. Okay, now this main. Okay, so we don't have main. Okay, we have control column, and then we have the plot. And which model will do this better? Just ask to add styling to this thing. What are you doing? Yeah, what? In one styling inline. This is Claude 3.5 Sonnet. Yeah, this is nice, but added another comment there we don't need. Okay, added line styling. And make sure all items fit into the screen. Let's try 3.7. Okay, 3.7 is nice. It's nice, but we don't like it. Yeah, we don't want any of the reasoning models. What's on earth is 4.1? Let's actually go over them one by one. if there is enough space on the screen, expand all the basic, intermediate, and expert controllers. Just going back to GPT-4o.
Made changes.
Made changes. Because we actually know what to expect from it. Okay, I like the idea. Okay, let's see. So we have add inline styling, make sure all items fit into the screen, make sure it works on large and small, horizontal and vertical. If there's enough space on the screen, expand all the basic, intermediate, and expert controllers. They make sure the waveforms visible. Yeah, they should be taking up most of the screen. On the white screen, the controls and waveforms should be side by side. On a smaller screen, we want to still show the waveform in a large window and the controllers collapsed, so we just see the basics.
Made changes.
Made changes. Yeah, understand why it's not scaling in real time. That's okay. And let's go back for a sec. Oops. We're still ChatGPT 4.0. Also, if there is enough space on the screen, can we show all the 12 leads and then on mobile phone just show the 3?
Made changes.
Made changes. That's not good. Okay, now I'm actually, I don't think it was following instructions. Or 1, not sure. That's a reasoning model, should be thinking now. It added the script. Okay. Okay, it says 12 leads, but they're not actually there. Yep, on smaller screens it will collapse. It's actually pretty nice. Okay, or one it is. Okay, so when we make the screen larger, the 12 leads are being selected instead of the 3 leads, but the display actually still showing only 3 leads. Can you figure what's going on? That's so one thinking models that will take longer.
You need to dispatch a change event after programmatically checking the 12 lead radio button so the display actually.
Okay, so I have 3 with a collapsed control panel. once we go larger, the control panel is expanding. It's very nice. Yeah, love it, like it. Probably could be other improvements to it, but let me know what you think. Yeah, I would have expanded that sooner. Yeah, one seemed to understand what's going on pretty well. Okay, can we do the same thing for the export expandable menu on a larger screen? Can we just expand it and on a smaller screen collapse?
Made changes.
Well, you made changes, but you got rid of all the code as well. Made changes. Made changes. Now what are you doing? Keep the rest of the code as is. Silly little goose.
Made changes.
Made changes. Where did I say get rid of the rest of the code? Yeah, for the export extendable, export extendable menu on largest screen. Can we just the language, and on the small screen collapse. keep the rest of the code as is. Should be a simple task. Let's go Claude 3.7. Hopefully it won't get rid of the rest of the code. Hey, for real? Are you for real? To understand what the problem is, Copilot, add file to chat, new chat. Same prompt, GPT-4o. Okay, the script. Bum, 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 bum. Is that the thing it was giving me? Yes, so if we apply, should in theory going straight into, yeah, kept the code. I didn't finish generating. Silly little goose. Okay, it's working. The chat was able to sort it out, but when you edit the whole code, then it's stuffing things up. Okay. So generally, yeah, let me know. What do you think? Is it ready to be published? Yeah, there's this funny business. There is this funny business about the waveforms, the box where the waveforms are displayed, whatever it's called, that it's getting too small. We might want to set minimum size for it.
Collecting workspace information. The box where the waveforms are displayed is likely the AND LT, div and GT, with the ID equals grid. Inside the AND LT section.
Yeah, we don't want to add the style that way. We want to is it called grid? Can we add the minimum width? Three 0.7. Again, on the different problem, I don't know how to solve it. Because that's how it will look like on mobile. Pa, pa, pa. Okay, I think we spent enough time on it. Don't think we'll be able to improve it further.
Here are some suggestions to improve the styling of your page. 1. Responsive design. Use CSS media queries to Solution explanation, step by step. Identify where the final explanatory text is, near the bottom of index.html. Insert additional paragraphs beneath the existing How to Use This ECG Simulator section. Provide more detailed descriptions of the controls, referencing labels and sliders. Keep the rest of the code as is, only adding new paragraphs for clarity. Index.html. Add a more extensive
Okay, so we want a more detailed overview at the bottom of the page. Hey, can you include topics like the difference between synthetic and real data, and how synthetic can be potentially better? Hey, can we also add a disclaimer that the presets might not be accurate, the different disorders, and give an overview of the disorders we covered, the abnormal ECG waveform types that we cover. Don't mind you to go into the weeds on that one.
Solution explanation, step by step. Identify the bottom of index.html.
Yeah, that's fine. That's a reasoning model, so it's explaining what it does. That's fine. And we need to get remove source, delete, add, copy text. We'll add that description. That's the new description. It's not published yet. Okay, so it's generating essentially a podcast on it. The mind map can be helpful as well. So we have the mind map is actually interesting. Let's close it for a sec. Yeah, it's still generating the podcast. We can watch bees while we wait. Need more explorers, don't we? More explorers. Those are pheromone traces for the worker bees to follow. Can add more flowers, but we don't have explorers, so the workers would not find those flowers. Guess we have 13, 14 minutes ready. Shall we let them chat, or are we doing interactive? Interactive, let's do interactive mode.
You know, when you look at an ECG trace, those little waves, it's like reading a secret code from the heart. So much information packed in there.
It really is, and understanding it deeply can be challenging.
Which is why today we're doing something a bit different. We're not just looking at static images. We're actually going to, get our hands dirty with the tool that lets us build and change these waveforms.
That's right, we're diving into an ECG simulator. We've got information on its features, how it works technically.
And our mission for this deep dive?
It's to really critically examine how this simulator allows for very detailed manipulation of synthetic ECG data. We want to understand the technical side, how you can tweak things, what those tweaks represent electrically, and what we can truly learn from that level of control.
Okay, so let's start at the beginning, the basic controls. What do we find there?
Well, first off, there's a preset menu. You get examples, things like normal sinus rhythm, but also various abnormal rhythms. It gives you a starting point.
And a BPM slider, beats per minute. So adjusting the heart rate, how does that actually look on the trace when you slide it?
Yeah, the BPM slider adjusts the overall rate. Slide it up, the whole cycle P wave, QRS, T wave speeds up, everything gets closer together on the screen.
More crowded looking?
Exactly. Slide it down, it stretches out, you see the intervals more clearly. It's a very fundamental way to see that inverse relationship between rate and cycle length.
Simple but effective. Then there's this add noise toggle. It mentions simulating real-world conditions. What kind of noise are we actually adding here?
Right. Real ECGs are almost never perfectly clean, are they? You get interference, muscle tremor, electrical noise, movement.
Sure.
So this toggle likely adds some random signal variation, maybe some baseline wander or high-frequency noise. Adding it helps you appreciate how noise can, well, obscure the important parts of the ECG. It shows the challenge of signal processing in real life.
And the default view shows the 3 limb leads, 1, 2, and 3. Why start with just those 3 from a technical standpoint?
The limb leads, they form Einthoven's triangle, the classic view. They're derived from electrodes on the arms and legs. Okay. And they give you that crucial first look at the heart's electrical activity in the frontal plane. Lead 2 is actually the sum of I and 3. Mathematically, you calculate the heart's main electrical axis from these. They're foundational.
Got it. So moving up a level, we have intermediate controls, specifically timing sliders for PR, QRS, and QT intervals. Let's break those down. What exactly are we adjusting?
Okay, these are key intervals. The PR interval is the time from the start of the atrial P wave to the start of the ventricular QRS complex. It reflects how long it takes the signal to get through the AV node.
Right, the delay point.
Exactly. The QRS duration is the time for the ventricles themselves to depolarize, to activate.
And QT.
QT covers the whole ventricular process, depolarization and repolarization, so activation and recovery. Being able to adjust these timings in milliseconds lets you simulate things like AV blocks by lengthening the PR interval.
So you could model a first-degree block, for instance.
Precisely. Or you could widen the QRS to mimic a bundle branch block, where ventricular activation is slower or takes an abnormal path.
And changing the QT interval.
That's critical because it relates to ventricular repolarization. A longer QT can indicate risk for certain dangerous arrhythmias. So this fine-tuning lets you directly see how these specific electrophysiological changes look on the ECG trace.
Very powerful for visualization. There's also a window length control here. How does changing the amount of time shown on screen help technically?
The window length is about perspective. A short window, maybe just a few seconds, gives you a zoomed-in view. Great for measuring intervals accurately, looking at the shape, the morphology of individual beats.
Close-up detail.
Right. But a longer window, maybe 10, 20 seconds or more, shows you the bigger picture. You can see the rhythm over time, spot irregularities, ectopic beats, look at variability. It's a trade-off, detail versus context.
Makes sense. Okay, let's step up to the expert controls. The description mentions things like Mobitz block parameters. This sounds like really deep manipulation.
It is. The expert controls let you fiddle with the parameters behind more complex heart rhythm problems. Mobitz blocks are types of second-degree AV block, where some atrial beats just don't get through to the ventricles.
So you can control how they fail to conduct.
Likely, yes. You could probably set the probability of a dropped beat Or maybe simulate the specific pattern of PR lengthening seen in Movit's type I versus the fixed PR before a drop beat in type 2. It's moving beyond just interval lengths to simulating conduction probabilities and patterns.
That's quite sophisticated. Another expert control is the ST offset slider. It says it's useful for visualizing things like STEMI or end STEMI. How does shifting that ST segment help understand ischemia?
Okay, the ST segment, that flat line between the QRS and the T wave, is super sensitive to lack of blood flow, to ischemia.
Right, that's a key diagnostic sign.
Exactly. In a stimming ST elevation MI, that segment elevates. In instant I, it might depress. This slider lets you manually push that segment up or down relative to the baseline.
So you can simulate the visual effect directly.
Yes, and quantitatively, you can see how much elevation or depression is significant. It helps visualize those critical diagnostic signs for heart attacks.
And finally, under expert, we have these noise source sliders for white, 50 hertz, and motion noise. Why separate them out like this?
This is about realistic artifact simulation. White noise is just random background fuzz, equal energy everywhere. 50 hertz noise, or 60 hertz in some places, is that specific hum from electrical power lines.
You see that a lot on real traces.
You do. And motion artifact is usually lower frequency, baseline sway, caused by the patient moving or breathing. Being able to mix these independently lets you create much more realistic noisy signals.
So you can see how different types of noise affect the trace.
Precisely. You can learn to recognize the signature of each type and understand how different noise sources might obscure or even mimic pathological findings. It highlights why artifact filtering is so important.
Okay, let's shift gears to how the data is actually shown. There's a 12 leads view, usually in a 4x3 grid. Why is moving from those initial 3 leads to 12 so important technically?
It's about getting a 3D picture, essentially. The 12 leads add chest electrodes, giving you views of the heart's electrical activity from different angles, including the horizontal plane, not just the frontal plane like the limb leads.
A more complete electrical map.
A much more complete map. It allows for better localization. You can pinpoint where an MI might be occurring or where an arrhythmia is starting. It's just much richer spatial information for analysis.
And if you want the raw data itself, there's an export function, CSV or PNG. Let's look at the CSV. Time S plus 12 leads, MV, 250 hertz sample rate. What does that spec tell us?
Okay, that's packed with technical info. Time S means each row has a timestamp in seconds. 12 leads MV means for each timestamp you get the voltage in millivolts for all 12 leads simultaneously.
And the sample rate, 250 hertz.
That's crucial. 250 hertz means the simulator is taking 250 measurements, or samples, every second for each lead. This determines the digital resolution. Higher frequency means you capture faster electrical changes more accurately. 250 hertz is fairly standard for clinical ECGs, though higher rates exist.
So it defines how detailed the digital version of the signal is.
Exactly.
The PNG export seems simpler, just an image of what's on screen.
Pretty much a snapshot. Useful for saving a visual record, putting it in a presentation, comparing setups quickly, straightforward image capture.
It also mentions that calibration pulses are omitted for clarity. Why leave those out in a simulation?
Calibration pulses on a real ECG machine are those little square waves, usually 1 millivolt high. They're there to check the machine's scaling is correct.
Right, to make sure 1 MV looks like 1 MV on the paper or screen.
Yes, but in a simulation, the voltage values are generated by the code itself. They are, by definition, actionately scaled within the simulation. Adding a calibration pulse would just be redundant data clutter. Doesn't add value here, so omitting it keeps the output cleaner for analysis.
Okay, it makes sense. Let's touch on the tech behind the scenes. It says every regeneration runs in a web worker for smooth sliders. What does that mean architecturally?
Ah, web workers. That's a smart design choice for web apps. A web worker is like a background process for your browser.
So it doesn't freeze up the main page.
Exactly. Calculating and redrawing ECG waveforms, especially when you're dragging sliders quickly, takes computational effort. If you did that on the main browser thread, the user interface, the sliders, the buttons could become laggy or unresponsive.
Annoying on a desktop, probably unusable on mobile.
Right. By putting the ECG generation in a web worker, it runs separately. The main thread stays free to handle your clicks and drag smoothly. It's key for making interactive tools like this feel responsive.
Now, probably the most critical point, the disclaimer. It stresses these are synthetic signals, should not be used for clinical decisions. Why this strong warning? What are the real limits here?
This is absolutely vital. The simulator uses algorithms, mathematical models. They are simplifications of incredibly complex biological reality.
They aren't real heart signals.
Not even close in terms of the underlying biological fidelity. Real physiology has layers upon layers of complexity, individual variation, influences from nerves, hormones, disease states, things a model can't fully capture. Using simulated data to diagnose a real person could lead to serious errors. It's dangerous.
The simulator is for learning principles, not patience.
Precisely. Learning principles, understanding relationships, but not clinical application.
The disclaimer also mentions that even though synthetic data is clearer, it may not perfectly reflect all the nuances of real medical data. What kind of nuances are missing?
Oh, lots. Think about subtle changes in wave shapes due to slight rotation of the heart or the effect of breathing on the signal baseline. Think about very specific complex morphologies of rare arrhythmias, the subtle ways medication can alter the trace.
Things that require experienced human interpretation.
Exactly. Real ECGs are often noisy, have baseline drift, show combinations of findings. The simulator gives you idealized, cleaner versions. It's good for isolating concepts, but doesn't train you for the messiness of reality.
It also specifically calls out presets like STEMI or atrial fibrillation as general approximations, saying real cases vary hugely. Why simplify them so much?
Well, you have to simplify to make it teachable in a simulator. The STEMI preset will show clear ST elevation, maybe in the expected leads for a certain infarct location. The AFib preset will show irregular rhythm and no clear P waves.
The textbook examples.
Textbook examples, yes. But in reality, a STEMI might have subtle elevation, or be confounded by a bundle branch block. AFib might have periods of regularization or varying ventricular rates. The presets show the core concept, but if you only learn the preset, you might miss a real, more complex case.
So relying only on these idealized presets could actually be misleading later on.
It could lead to a false sense of confidence or an overly narrow view of what these conditions look like. You absolutely need exposure to real, varied clinical data alongside using a tool like this.
Which reinforces the point about consulting authoritative medical resources or professionals for real interpretation.
Absolutely. The simulator is a fantastic educational aid, a supplement. It is not and should never be treated as a replacement for proper medical training, clinical experience, and expert resources.
Despite all those crucial caveats, the text does praise it as a fun, educational way to see how changing parameters affects the ECG. It encourages playing around, making custom arrhythmias. What makes this interaction so valuable for learning?
It's the immediate feedback. You tweak the PR interval, you instantly see the change on the waveform, you introduce noise, you see how it affects clarity, this active experimentation, this cause and effect exploration in real time.
It connects the abstract concept to a visual output.
Exactly. It builds intuition in a way that just reading a book or looking at static diagrams often can't. Being able to break the normal ECG in specific ways and see the result helps solidify understanding of the underlying physiology and pathophysiology.
So, wrapping up this technical deep dive, we've seen how this ECG simulator offers quite detailed control over synthetic waveforms.
Yeah, from basic rate and noise through precise interval timing up to simulating complex blocks, ischemic changes, and specific noise types.
We've also looked at the data itself, the 12-read view, the export specs like sample rate, and why things like calibration pulses are omitted.
And critically, we've spent time on the limitations. The synthetic nature, the simplifications, and the absolute necessity of not using this for clinical judgment. It's an educational tool, period.
Right. That distinction is paramount. It's a powerful way to learn about ECGs, not to read real ones for patients.
Definitely.
So thinking about the level of technical detail and interactive control we've discussed here, it makes you wonder, what's the future for these kinds of sophisticated simulation tools in medical education or even research? How far can we push this simulation while always keeping that critical eye on the gap between simulation and the complex reality of biology?
That's the big question, isn't it? How to leverage the power of simulation responsibly.
Something for us all to think about. Thanks for digging into the details with us today.